Hey guys, this is Mr. Hastings right here, and we're going to be going over exponent laws, and this will be something that maybe if you struggled with before, this will kind of help you catch up, and we can get you up to that star level where you understand exactly what's going on. So, first, I want to start over with some basic rules. We're actually going to start about what happens when we multiply bases that have the same variable. So, for example, what if we did x to the 3 times x to the 2? Well, x to the 3 times x to the 2 is actually going to give us x to the 5. And so the rule is, whenever we have the same bases, or multiplying those bases, we're going to add the exponents. So let me even write that first part. When we multiply the bases, we want to add the exponents. And so we know that 3 plus 2 gives us 5. All right. Now, what if we did the exact opposite? Instead of multiplying the bases, what if I did something like x to the 6 divided by x to the 4? Well, since division is the opposite of multiplication, what would be the opposite of addition? Well, right here we would have to go ahead and subtract. And so we know that x to the 6 minus 4 will really give us x to the 2. And so our basic rule is going to be this. When dividing by the same base, we subtract the exponents. Okay? So once again, the rule is when dividing by the same bases, we want to subtract the exponents. Now, our very next rule, well, here, I'll wait. We'll just have to edit that out. The very next rule that we're going to talk about is going to be the power rule. What happens when we have an exponent raised up to another exponent? And it could look something like this. What if we had x to the 3 raised to the power of 4? Well, we've already talked about addition. We talked about subtraction. Here, the next logical thing would be to multiply. We know that 3 times 4 gives us 12. So, for a power to a power, we multiply the exponents. For a power to a power, we want to multiply the exponents. Now, we're 3 rules in. We have just 2 more rules to go. All right, so here's going to be our 4th rule. And what happens whenever we have a negative exponent? Like, let's say we have negative x to the negative 3. Well, whenever you see any variable or constant or any number, we're always assuming it's actually over 1. It's like there's an assumed fraction bar over 1. In order to change a negative exponent to a positive, no matter if our exponent is on the top or on the bottom, we always have to move it to the opposite side. So, if this is on the top, we have to move it to the bottom, absolutely. And so what I'll do is I'll draw an arrow down here, and I will go ahead and cross that out. And what this really becomes is x to the, not negative 3, but the positive 3. Perfect. And so really what happens, because this top part is now empty, we assume that there's a 1 there, and it's 1 over x to the 3. Let's try another one of these. What if we had something like x to the negative 8? Well, once again, we're assuming that it's over 1. We're going to take it from the top to the bottom. And so what we'll really have is our x to the, not the negative 8, but now the positive 8 on the bottom. And what should we use as a placeholder? Well, we need that imagined or assumed 1 right there. And so this is what we're going to say our rule is. To change a negative exponent to a positive, we move it from the top or bottom to the opposite side. Okay? In order to change a negative exponent to a positive, we want to move it from the top to the bottom, or vice versa, from the bottom to the top. And we'll see some more examples like that in just a moment. Now, what if you ever see the exponent to the 0 power? Well, this is actually pretty common to see this, and a lot of people will always say that it equals 0, and they would be wrong. Anytime you have any number raised up to the power of 0, it will always equal 1. And so that's just going to have to be one of these facts that you really remember. But let's write this down. Any term to the power of 0 equals 1. So it does not matter what it looks like. Anything to the power of 0 equals 1. Now what I want to do is I want to take these 5 basic rules, and I just showed you these at the lowest level. I now want to start combining these into more challenging and more complex problems. So hopefully by the 5th problem, you'll be able to see how do all these rules work and kind of intertwine together whenever we have just a combination of all these factors. So problem number 1 here, we have 9x to the 3, y squared, divided by 3x to the 5, y to the, well, whenever we don't see an exponent, we always assume it to be a 1, absolutely. And so we now have this problem. Now, we know that when we see a fraction bar, that actually means to divide. And so we really have 9 divided by 3. And I want you to remember this statement. Normal numbers behave normally. So whenever we see 9 divided by 3, well, that's the same as 9 divided by 3. It's just a normal operation. So we know 9 divided by 3 is going to be 3. Now next we're going to look at x to the 3 over x to the 5. And I want you to think back to our rules. When dividing the bases, we subtract the exponent. And so we know we really have 3 minus 5. And I can write that down here as x to the 3 minus 5 will give us negative 2. Now let's go ahead and look at our y's. We really have y to the 2. It should be 2 plus 1 or 2 minus 1. Well, since we are dividing, we know that we want to subtract 2 minus 1. It becomes y to the positive 1. Now this is almost complete. However, there's one thing that we can never have. We can never have negative exponents. So remember our rule, in order to get rid of negative exponents, no matter where that value is, we have to move it to the opposite side of our fraction. And so we'll assume that 3x to the negative 2, y to the 1 is really all over 1. And because we have a negative exponent, we want to take this from the top and move it down to the bottom. And so what should our final answer look like? Well, we always want to ask ourselves, should it stay in the same place or should it change? We know this 3 is on top, but it has a positive exponent, so I'll leave it on top. Our x had the negative exponent, so we move it to the bottom where, instead of being a negative 2, it becomes a positive 2. And then right here we have y to the 1. Well, it's positive. So should it change or stay the same? It absolutely should stay on top. And so our final answer is going to be 3y all over. Now for problem 2, we have this. We have 9x to the 3rd, y to the 7, and z. And once again, wait a second. Whenever we don't see an exponent, what should we automatically write? 1. And so right here we now have that multiplied by 2x to the 4th, y to the 8th, z to the 8 as well. Now check it out. Remember our say, normal numbers behave normally. And so we really have 9 times 2, which is 18. And now we have x to the 3 times x to the 4. And what's our rule? When multiplying the bases, we should add the exponents. And so we really have 3 plus 4, which gives us x to the 7. Now we have y to the 7 times y to the 8. We're still multiplying, so 7 plus 8 is going to actually give us y to the 15. And now we have z to the 1 times z to the 8, and we know that that 1 plus 8 is going to give us z to the 9. We're done. Alright guys, now let's go ahead and look at kind of a combination problem where we have both multiplication and division. Now, personally, the way that I would like to attack this is I usually like to do my multiplication across the top and then do my division. I find that that's a little bit easier. And so let's see, what would that look like? Well, right here, across the top, we know we're doing our multiplying. And we know that normal numbers behave normally. And so what is 9 times 3? Well, right here, we're going to say 9 times 3 is 27. We would then want to go ahead and look at our x's. We have x to the 3 times x to the 5, and remember our multiplication rule, when multiplying the same bases, we want to add the exponents. And so we really have 3 plus 5, which gives us x to the 8. Now from here we have y to the 4 times y to the 2, and we know that we will add when multiplying the bases. So 4 plus 2 gives us y to the 6 all over. And then you have to ask yourself, should this bottom stay the same or should it change? Well, there's nothing going on here, so we're just going to copy it exactly as we see it. We have 7x to the 10, y to the 3. Now, from here, what we want to go ahead and do is we want to go ahead and use our division rules, and I cannot stress this enough. Normal numbers behave normally. Now, we see 27 divided by 7. I want to ask y'all, can 27 be divided by 7? Well, the answer is no. So whenever you have these fractions with these normal numbers, I would suggest putting in your calculator 27 divided by 7 and see what the calculator reduces it to. Well, in this case, it actually cannot reduce, and so when we drop down to our next line, we want to draw our line, and we'll leave it as 27 over 7. Now from here, we see our x to the 8 over x to the 10, and when dividing, we want to subtract the exponents. And so we know that 8 minus 10 really gives us x to the positive 2? No, wait a second. 8 minus 10 really is the negative 2. Perfect, perfect. Guys, make sure that you are accounting for your negatives. And if you have to, use the calculator. There's no shame in that. Now we have this, y to the 6 over y to the 3. Well, it's really 6 minus 3 gives us y to the 3. Now once again, we have to ask ourselves, is there anything here that we need to fix? And the one thing that's wrong is we cannot have a negative exponent. And if our negative exponent is in the top, we want to move it to the bottom. And so right here, let me just go ahead and write this next round. We'll write 27 over 7. We know they stay. But how about this x to the negative 2? Well, it's on the top. I write it on the bottom as x to the positive 2. We know on top we have y to the 3rd. And there's our final answer.